welcome to the Explainer. Today, we're jumping into the awesome invisible world of chemical reactions. We're going to break down how everything around us is constantly changing, from the fizz in your drink to the flash of a firework. So it really all starts with just looking around. Ever see something burn or rust or fizz and just wonder what's actually going on in there? That dazzling light from a firework, the rust on an old bike, even just a tablet dissolving in a glass of water. Yep, those are all chemical changes, and we're about to pull back the curtain on the science behind it all. Okay, check this out. This is a classic example. When this magnesium ribbon burns, it's not just vanishing into thin air. Nope, it's actually reacting with the oxygen all around it and turning into something totally new, this white powder, which is magnesium oxide. And that incredible blinding light, that's our first big clue that a massive transformation is happening right down at the atomic level. All right, so here's the game plan for today. We'll kick things off with the basic language of change. Then we'll cover the signs to look for in a reaction, tackle the great balancing act, and meet the different reaction families. After that, we'll dive into redox, the electron trade, and wrap it all up by seeing how this chemistry shows up in your everyday life. Okay, first up, the language of change. See, to really get what's going on with chemical reactions, we've got to learn their language. And it really just boils down to two things, the stuff you start with and the stuff you end up with. So at its heart, a chemical reaction is really just a transformation. The ingredients you start out with, we call those the reactants. And after they do their thing, rearrange their atoms, they become completely new substances. And those, we call them the products. It's that simple, from reactants to products. That's the whole journey right there.
All right, so that's the theory, but how can you actually tell a reaction is happening? The cool thing is, you don't need some fancy microscope. You just have to know the signs, the 5 big clues to look out for.
And this table here lays them out perfectly. You might see a change in color, right? Like that first example. Or you might feel things get hot or cold. That's a change in temperature. Sometimes you'll see a change of state, like 2 gases coming together to make a liquid. Or, hey, maybe you see bubbles. That's the evolution of a gas. And the last one, which is really cool, is when a solid just kind of appears out of nowhere in a liquid. Chemists call that the formation of a precipitate. Any one of these is a dead giveaway that atoms are being rearranged. Okay, let's get to a really big idea. Every single chemical reaction, no exceptions, has to follow one fundamental, absolutely unbreakable rule. It's what we call the great balancing act of chemistry.
And that rule is this: mass can't be created or destroyed. That's it. It means that in any reaction, atoms don't just appear or disappear, they just get rearranged. So whatever you start with, you have to end with. The total weight of your reactants has to exactly equal the total weight of your products. Nothing just vanishes.
So to make sure we're following that law, chemists have to balance equations. Think of it like a puzzle, and these steps here are your cheat sheet for solving it. It's all about counting the atoms on both sides and making sure they're equal. You use these little numbers called coefficients out in front of the formulas to make it all add up. It's how we prove, on paper, that we're respecting that law of conservation of mass every single time. All right, now that we've got the rules down, let's start sorting these reactions out. I mean, there are a bazillion different reactions, but the good news is most of them fall into just a few main families, and each family has its own unique pattern. So let's start with 2 that are basically perfect opposites of each other. First, you've got combination. That's where 2 or more things come together to make one single, more complex thing. A plus B gives you AB. Simple. Then, on the other side, you have its exact opposite, decomposition. That's where one thing breaks apart into smaller, simpler pieces. So AB splits back into A and B. And this is a fantastic example of decomposition in action. It's called electrolysis. What we're doing here is using electricity, see the battery, to literally split water molecules apart. The electric current breaks H2O down into its basic parts, hydrogen gas and oxygen gas. And you can see them bubbling up and getting collected in those 2 separate test tubes. Pretty cool, right? Okay, next up, we have the displacement reaction. And I love this analogy. Think of it like a dance partner swap. So you've got a couple, BC, on the dance floor. Then this new element, A, comes along. Now, if A is more reactive, a better dancer maybe, it cuts in, steals C for itself, and kicks B off the dance floor. So you end up with AC, and poor B is left all alone. And what's really cool here is that we can see exactly why this happens. So on the left, you see the reaction. Zinc is kicking copper out. Why? Well, look at the chart on the right. That's the reactivity series. If you find zinc on that list, you'll see it's way higher up than copper. That means it's more reactive. This chart is basically a cheat sheet that tells us who's going to win the chemical dance-off every time. And if one partner's swap is good, why not two? That's a double displacement reaction for you. It's exactly what it sounds like. You have two couples, AB and CD, and they just switch partners. A ends up with D, and C ends up with B. It's like a big chemical square dance where everybody gets a new partner. All right, let's zoom in on what is maybe one of the most important types of reactions in all of chemistry. Seriously. They're called redox reactions, and it all comes down to a trade of these tiny little things called electrons. Now, the most important thing to get about redox is that you can't have one part without the other. They always happen together. Basically, one thing loses electrons and another thing gains them. The loss of electrons, that's oxidation, and the gain of electrons, that's reduction. A super easy way to remember it is oil, rig. Oxidation is loss, reduction is gain. They're two sides of the same coin, a perfect give and take. And here's a perfect picture of it. You start with zinc oxide and carbon. Now watch what happens. The zinc oxide loses its oxygen, so we say it's been reduced. And where does that oxygen go? Well, the carbon gains it, so the carbon has been oxidized. See? One loses, one gains. That's redox. So who cares, right? Why does all this redox stuff matter? Well, it matters because oxidation is one of the most common chemical reactions out there, and it affects our daily lives constantly, in both good ways and, well, not so good ways. I mean, you see the effects of oxidation literally everywhere. That rust on an old car, that's iron oxidizing, we call it corrosion. The black stuff on old silverware or that green coating on a copper roof, yep, also corrosion. And it's not just metals. Ever eaten stale chips? That gross taste is from the fats and oils oxidizing. We call that rancidity. But here's the cool thing. Since we understand the chemistry, we know how to fight back. We paint metal to block the oxygen. We put our food in airtight containers to, keep the oxygen out. And food companies even add things called antioxidants to slow the whole process way, way down. So when you really think about it, from a roaring fire to a slowly rusting nail, our world is just this constant buzz of chemical conversations. And now that you know the language, you can spot the signs, and you understand the rules, what are you going to see differently? What kinds of amazing transformations are you going to notice now that you just didn't see before? Hey, welcome to The Explainer.